Greetings, math people, and this is lesson 5 of differential equations. Today we're looking at first order linear differential equations, and we'll be solving them using integrating factors. So let's go ahead and get right into it.
Specialized in science and math, original black men, busting thoughts that pierce your mental, the fierce, ripping your section. Vocal toe to toe, impeccable, splitting your back, son. Simple as addition and subtraction, black thought, the infinite relaxed one.
All right, so we're starting to get to the good stuff into this differential equations course. So let's first outline what a first order linear differential equation looks like. So a first order linear differential equation will be of the following form. So dy by dx plus p of x y equals q of x. So it's called linear. So the linear, the other terms in the name, first order differential, you know what those mean already. It's called linear because of this y term. So in these equations, this will just be y. It won't be y squared. It won't be y to the 3/2 power. It'll just be y, and it'll be multiplied by a function just of x. So this function, p of x, need not be linear. It could be any type of function as long as it's a function of x. It can also be a constant function. And this q of x also, it should just be a function of x. Again, it can also be a constant function. It could be 0, making it homogeneous. And a q of x is sometimes called the forcing function or the input or the non-homogeneous term. All right, so this is the general form of a first order linear differential equation. And so everything we talk about doing today, the methods of solving we'll discuss, will be based off a differential equation of this form. Now, sometimes it may not be given in this form initially. As long as we're able to rewrite it in this form, then it fits this particular package. So we're going to solve this using something called an integrating factor, which I'm going to explain somewhat in reverse, meaning I'm going to tell you what the integrating factor is and then show you why it's useful. So the integrating factor, which I'll call u of x, is going to be e to the power of the integral of p of x dx. And p looks a little shady there. I think you know my intention. So that's the integrating factor. And what it allows us to do, so it makes solving this, basically we're trying to solve for y. It makes solving for y easier by multiplying by this integrating factor because it makes the integration easier. So let me show you what I mean. So I'm going to multiply everything in this equation by e to the power of p of x dx. And just be careful about signs here, because some books will put the p of x over here sometimes, or even some problems of p of x may be moved over there. Now, if the p of x y is on this side, then this integrating factor will have a negative sign here. So just be careful about the sign. So you may see it presented a little differently in maybe some different books. So here, the way I'm presenting it and the signs I'm using, if the p of x y term is on the left-hand side of the equal sign. All right, so what I'm going to do is I'm going to multiply everything by e to the power of the integral of px dx. And what I'll get is e to the power of integral p of x dx times dy by dx plus e to the power of the integral of p of x dx times p of x y, and that will equal, e to the same power times q of x. Now, This may not seem like this made the problem simpler, to you, it may have made the problem more complicated. All right, but I want to concentrate on one part. So I want to concentrate on this. As nasty and as yucky as it may seem, I want to look at this part. Now, I'm aware that I'm out of paper, so I'm going to come back to this, but I just want you to take a look at this part right here. And what I'm going to do is I'm going to write u of x times y. Now, again, u of x is e to the power of the integral of px dx, so times y. And what I'm going to do is I'm going to take the derivative of this with respect to x. Now, this is a product of two functions, and so I'm going to utilize the product rule. So the first thing I'll do is I'll leave this guy alone and take the derivative of this. So I'm going to leave this guy alone, so that will give me e to the power of the integral of px dx times the derivative of y with respect to x, so that's dy by dx, plus, now I'll take the derivative of this guy and I'll leave the y alone. Now understand the derivative of this guy is going to use the chain rule. And so I guess I'll write out, I was going to do it mentally, but let me just write it out. So let's say I make u equal the integral of px dx. So this derivative would just be p of x. And this would give me e to the u, and its derivative would be e to the u. So then this derivative is e to the power of the integral of px dx times p of x, excuse me, and then we're leaving this guy alone. Now, if you notice, let me bring this other paper back. What we have here is the same thing we have here, which means that this term, well, not term, this expression here is simply u of x times y prime. So this expression here is u of x, our integrating factor, times y prime, if you will, because we get this by taking the derivative of u of x times y with respect to x. Now, why is that important to point out? Because if we integrate this, so if I integrate this whole expression, this whole guy right here, is the guy you see boxed up, what I'm going to get is u to the x, y. So let me rewrite this on a separate sheet. So this whole expression here. So the expression is e to the power of the integral of p of x dx times dy by dx plus e to the integral of px dx times p of x y equals e to the power of the integral of p of x dx times q of x. All right. So once I've multiplied by this integrating factor, so that's what you see here. So this was the expression multiplied by the integrating factor. Again, remember this is simply the derivative of y times the integrating factor. So after that point, I can integrate both sides. I can integrate both sides. And now, again, please remember that this was simply the derivative of y times this, y times u of x, which is e to the power of px dx. So if I integrate it, since this is that derivative, if I integrate it, then I'm just going to get e to the integral of px dx times y. And of course, that'll equal this integral. So this is the integral of e to the integral of px dx times q of x, right? Plus some constant. And now remember, our objective in solving these differential equations is simply to solve for y. So to solve for y, all I have to do is divide by this, or you can say multiply by e to the power of negative integral px dx, which means y would be e to the power of negative integral px dx times the integral of e to the integral of px dx times q of x dx plus c times e to the negative integral of px dx. All right, now what you see right here is actually the solution to a first order linear differential equation of the form we spoke of. We do not recommend you memorizing this formula. What we recommend you, really the only thing that will be important in terms of solving this for you to remember from pure memory is the integrating factor is e to the power of the integral of px dx. Because what we'll do in practice, we kind of work this out here, but what we'll do in practice is we'll multiply by the integrating factor and then go ahead and integrate and solve the problem. So we won't use this formula here. We'll go through the process and that we went to get this formula in a sense, if that makes any sense. Now, one thing I want to point out before I do several examples is that the solution to a first order linear differential equation, so this guy, so let's say I call this guy 1. The solution to 1 is the solution to the associated homogeneous differential equation. So the associated homogeneous differential equation is if q is equal to 0. So it's that solution plus what we call the particular solution to the differential equation. And I want to quickly just show you the solution to the associated homogeneous situation, because you'll see it within this solution here. So again, this is our 1 here. That's our general form of our first order linear differential equation. So let's say I take this guy and I'm making q 0, right? So we call this the associated homogeneous equation. So it's, homogeneous when it's equal to 0. So I'm making this equal 0. Now imagine me solving this guy if this is 0. To solve this, if this is 0, it's really just a separable differential equation. So if you will, if I separate, I would move this to the other side. It would be negative p of x, y. And then I would do the separation where the y will go here. So it will be dy over y. And that will equal negative p of x dx. So again, I first move this over here, negative p of x, y. Then I move the y over here and the dx over here. And then of course, if we integrate, we'll get ln y equals the integral, put the negative sign on the outside, of negative p to the x dx. And we'll exponentiate, of course, to solve this for y. And so y, I should say plus some constant, plus some constant. So y would be e to the power of the negative integral of px dx, to also times e to the power of c, which is just c. So the solution to the associated homogeneous first order linear differential equation would be this guy, correct? And if you look at this long drawn out solution that we had, so you'll see that guy here. So this is called the solution to the associated homogeneous equation, which sometimes you'll see referred to as y of h. And this, all of this, is called the particular solution, which sometimes you see written as y of p. All right. But we don't have to worry about doing each of them. Like, I don't have to worry about doing a homogeneous equation, solving it, and then solving the whole guy, because when I do this integrating factor process, it's going to give me both these guys. All right. So I hope that made sense. Again, the key thing in this process is just understanding. So I'm going to put it up again, understanding that the integrating factor is e to the integral of px dx. And we're going to multiply everything in the equation by the integrating factor. And when we do that, the stuff that we have on the left, well, that is just the derivative of the integrating factor times y. So when we integrate, we just get the integrating factor times y. That's the important part to really remember. All right, let's go ahead and just work through some examples. So some of these examples will be IVP, so have an initial condition. Some will not. Some will be written in Leibniz notation. Some will be written in Newton's notation, just to keep it diverse. All right. Let's solve some first order linear differential equations, shall we? All right, so here's the first example. And I have several examples. I don't know the exact number, but I know I have several examples, like 5 or 6 we'll go through. We should be able to go through them fairly quickly here. And so again, we want to make sure it's of the form of that equation that I called 1. And if it's not, we'll put it in that form. So this is definitely of the form. So my p of x here is 4. Again, I said p of x could be a constant. In this case, it's a constant. My forcing function, q of x, is x. And we do have an initial condition. All right. So the first thing we want to do is define and find our integrating factor. And so our u of x here would be e to the power of the integral of 4 dx. So that's just going to be e to the power of 4x. All right. So once we get the integrating factor, we're going to multiply everything by the integrating factor. And, it's somewhat trivial to multiply it by this, but I'm going to show multiply it by everything, because, again, when we multiply by this, what it's doing, and the reason we're doing this, is to make this just equal y times the derivative of y times the integrating factor. But let's go ahead and multiply everything by e to the power of 4x. And so we'll get e to the power of 4x times dy by dx plus 4e to the power of 4x times y equals e to the power of 4x times x. Maybe I should have put the x before the e. All right. So after we multiply by the integrating factor, we integrate both sides. So I'm going to integrate this guy, and I'm going to integrate this guy. Now, in normal situations, maybe an integral like this may look difficult, but our understanding of the problem is we understand that this is simply the derivative of y times u to the x. So this is the derivative of y times e to the 4x. So if I integrate, then I'm just going to get e to the power of 4x times y. So this part, integrating this one, will always be simple, because when you integrate it, you're always going to get your u of x times y. Simple. Now, this one over here, so to do these problems, of course, to do a lot of differential equation problems, you have to be very proficient in integration. And so the different techniques of integration. This integral here can be done by integration by parts. So let's say I use integration by parts, and let's say I let u I kind of want to do this. I kind of want to just write this little part on a separate sheet. So I'm going to write it underneath here. So let's say I let u equal x and dv equal e to the 4x, which means du would be dx and v would be 1 over 4 e to the 4x. And so thus this integral is u times v. So that's 1 over 4x e to the 4x minus the integral of v du. And so there's already a 1 over 4 there. And the integral of e to the 4x is 1 over 4 e to the 4x. So that'll give me minus 1 over 16 e to the 4x plus some constant. So this is what I'm going to get for this integral here. So let me write that. So this is going to equal 1 over 4 x e to the 4x minus 1 over 16 e to the 4x plus c. Now in this problem, this is an IVP. We have an initial condition where x is 0 and y is 0. So we can use that initial condition to solve for c. So let's use it real quick. So I'm gonna plug in 0 for x and 0 for y. 0 for every x, 0 for every y. This would be 0. This would be 0. This would be negative 1 over 16. So that means c is going to equal positive 1 over 16. So this implies that c equals 1 over 16. All right, so c is going to equal 1 over 16. And for the sake of space, to be able to finish this problem off on this paper, I'm not going to write a line with this as 1 over 16 and then, divide by this. I'm going to go ahead and divide by this. And as I'm dividing by this, I'm going to replace this with 1 over 16. So I'm going to divide everything. And of course, I'm doing this to solve for y by e to the power of 4x. And so here we will cancel this out. And that will leave me with 1 over 4x. And it will cancel this out. And that will leave me with minus 1 over 16. And remember, this c is 1 over 16, and I'm dividing by e to the power of 4x. So 1 over 16 e to the power of 4x. All right, we did it. That's our first example. And so this is the solution of the given first order linear differential equation here. So let's go ahead and do another example. All right, so here's our next example, and this one is written in Leibniz notation. Excuse me, this one is written in Newton's notation. And I'm a Leibniz notation guy. And so and a lot of times, if it's in Newton's notation, I'll rewrite it in Leibniz notation. I'm not sure if I'll do it here. I may not do it here, but generally that's my approach. I just like Leibniz notation. Now, the deal is this is not in the right form, however. So to put it in the right form, we're going to divide everything by x squared plus 1. And that'll give us y prime plus 2x y over x squared plus 1. And that'll equal 1 over x squared plus 1. All right, so now it's in the correct form. And so 2x over x squared plus 1 is like our p of x function. And this, of course, is our q of x function. All right, and so you might be looking at this and might think we're going to, integrate, get some type of arctan. It's really not going to happen, but it's beautiful to see this right here. Okay, so let's go ahead and establish our integrating factor. So again, our integrating factor is e to the integral of our px. Our px is 2x over x squared plus 1 dx. Now we can solve this with u substitution, if you will. We'll do it a little mentally. I don't think it's any need to write it out. I can make u equal x squared plus 1, which means du would be 2x. So it would be du over u. So that's ln u. So, and again, u was x squared plus 1. And so that means that this integral is ln x squared plus 1. I don't need absolute value because x squared plus 1 will always be greater than 0. fact, x squared plus 1 will always be greater than 1. And so e to the ln anything is anything. And so this is simply going to be x squared plus 1. So our integrating factor is x squared plus 1. So let's go ahead and multiply everything by x squared plus 1. Okay, so that'll give me x squared plus 1 times y prime plus not equal plus 2xy equals 1. All right, after we multiply by the integrating factor, we'll integrate. And of course, remember this integral is simply going to be u times y. So u was x squared plus 1. So x squared plus 1 times y. Of course, the integral of 1 is x plus some constant. There's no initial condition on this particular problem. And so the last thing we'll do is we'll just divide by x squared plus 1. So y would be x over x squared plus 1 plus c over x squared plus 1. I guess I could have just put x plus c over x squared plus 1. All right, so that's the solution for that particular differential equation. Let's look at our next example. All right, so just like the previous problem, this one is not in the right form yet. So we're gonna first put it in the correct form. So what I'll do is first simplify this expression here. And let's see, we'll get dy by dx equals y over x plus 1. We'll move this guy over to the other side. And so dy by dx minus, and I'm gonna write this as minus 1 over x times y equals 1. All right, and so now we'll find our integrating factor. I use a little of this side of the paper. So u of x will be e to the integral, so negative because of this negative sign, 1 over x dx. Of course, that integral is ln x, and of course, e to the, well, let me do this. So this integral is ln x, and so this is e to the negative ln x, which is e to the ln 1 over x. And of course, e to the ln anything is anything, and so this is going to equal 1 over x. So our integrating factor is 1 over x, so we'll multiply everything by 1 over x. Let's say I do it here, so I'm multiplying everything here by 1 over x. And so I have 1 over x dy by dx minus 1 over x squared y equals 1 over x. And so now we'll integrate. And again, remember when I integrate this guy, it's just going to be u of x times y. U of x is 1 over x. So this will be y over x. And the integral of 1 over x, of course, is ln x plus some constant. And then we multiply by x. And so we have x ln x plus cx. All right, that solves that particular first order linear differential equation. How many have we done? 2 or 3? I think that this might have been the third one, if I believe. Let's see how many I have left. 1, 2, 3. So 3 left. We're almost at 30 minutes. So let's try to make this a little bit quicker. Don't want to have an hour-long video. All right. Here is our next first order linear differential equation. It's in Leibniz notation. It's in the form we like. We don't have to move anything. There's no initial condition, so we can get right to this guy. So our integrating factor will be e to the power of 2x dx, which is e to the power of x squared. We'll multiply everything by e to the power of x squared. So e to the power of x squared dy by dx Now plus e to the power of x squared 2xy equals x times e to the power of x squared. And now we'll integrate. And of course, this integral is just going to be y times u of x. So that'll be y times e to the power of x squared. Now this integral, it may look like it's integration by parts, but it's just u substitution. And so I'll write a little bit of what I'm doing. So let's say u is x squared. That means du over 2 is x dx. So you see the x dx, that would be du over 2, and this would be e to the power of u. So the integral of e to the power of u is e to the power of u, and you have the 1/2 here. And so this is going to equal 1/2 e to the power of x squared plus some constant. And at last, we would just divide by e to the power of x squared. And so this will be 1/2 plus c over e to the power of x squared. All right. Let's go ahead and go to our second to last one, penultimate problem. All right, we have initial condition. It's not in the correct form right now, and it's in Newton's notation. So all the stuff we hate. All right, so let's first put it in the right form. So we'll divide everything by x, where y prime would be plus 1 over xy equals e to the power of x over x. All right. So let's find our integrating factor. And again, we have an initial condition that we'll deal with at the appropriate time. So our u of x will be e to the power of 1 over x dx. That's, of course, e to the power of ln x, which is just x. So our integrating factor is x. So we're going to multiply everything by x. And so this will be x times y prime plus y equals e to the power of x. So if you notice, once we multiply by the integrating factor, it actually went back to this form that the problem was initially in. But it's a beautiful thing. We'll go ahead and integrate. And so what that really means is, once you get a little more savvy, you may be able to recognize that this is of that form and understand that this is just, the product of your y times x, that this is just y times x, the product rule. And then you can just understand that and just integrate from there. But so let's go ahead and do what we got. So this is y times x, of course, and the integral of e to the power of x is e to the power of x plus some constant. So let's find our constant when x is 1, y is 1. So this will be 1, this will be e. And so that would be 1 minus e. C would be 1 minus e. So this implies that c equals 1 minus e. And let's go ahead and divide everything by x. And so y would be e to the power of x over x. And again, c is 1 minus e. So plus 1 minus e over x, if you will. All right, and yeah, I could have put the whole thing over x. All right, last example. So most of these problems were pretty straightforward. And again, our ability to integrate needs to be pretty sound when doing differential equations. There's nothing too crazy here. I think the worst we had to do was integration by parts, and it wasn't a bad integration by parts problem. Okay, so our final example. First, let's put it in the correct form. So let's divide everything by x. Minus 3 over x. Y equals x to the 4th. So u of x is going to be e to the power of negative integral of 3 over x dx. That's going to be e to the power of negative 3 ln x. And so I'm going to move this, make this negative 3 the exponent. So that's going to be e to the power of ln 1 over x cubed. And so which means I'm going to get 1 over x cubed. All right, so I'm going to multiply everything by 1 over x cubed. So I have 1 over x cubed dy by dx minus 3 over x to the 4th y. And that's going to simply equal x. We'll integrate. We'll integrate. All right, so this is just going to be y times u of x. What was u of x again? This is 1 over x cubed. So this will be y over x cubed. And this will be x squared over 2 plus some constant. And then we'll multiply everything by y cubed. And so we'll get x to the 5th over 2 times plus c times x cubed. All right, so that's going to conclude lesson 5, our differential equations. Lesson number 5, where we're doing first order linear differential equations. In our next lesson, lesson 6, we're going to be looking at first order linear differential equations again, but they will be with constant coefficients and a constant input. So hope you got something out of this. We'll see you next time.
Specialized in science and math, original black men, busting thoughts that pierce your mental, the fierce, ripping your section, vocal toe to toe, impeccable, splitting your back, son. Simple as addition and subtraction, black thought, the infinite relax one.